Hello everyone, my name is Zach Bracken and I'm a student at St. Mary's University of Minnesota, and today I'll be presenting on the effects of in utero atrazine exposure on musculus GST expression in relationship to circadian rhythm. In 2017, the EPA put out a study that showed that 3.88 billion pounds of toxins were released into the environment during that year. But as you can see by the figure on the right, that this number has stayed pretty constant throughout the past 10 years. But how it's been released in the environment was through air emissions, water discharge, disposal, etc. And these toxins often originate from the production of goods, car exhaust, pesticides, and herbicides, which brings me to my next point in atrazine. Atrazine is the second most commonly used herbicide in the US, only behind Roundup, and is used to prevent broadleaf and grassy weeds. The problem is that it's known to be water soluble and known to be an endocrine disruptor. That being said, it's already been banned by the European Union and is limited to 3 parts per billion in drinking water in the US. As you can see right over here, this is what atrazine looks like. So why should we be concerned with it? Well, as you can see, the red area is where atrazine has been found in high concentrations. That's because in the Midwest, there's a lot of cornfields, and atrazine is most commonly used on corn. That being said, it's allowed to be used on corn because corn has a detoxifying mechanism that allows it to break down atrazine. The detoxifying mechanism that is present in corn is glutathione S-Transferase, which is also present in humans. Glutathione S-Transferase is a metabolic detoxification enzyme, and there are 4 different classes of it, known as alpha, mu, pi, and theta. The one that's most specifically responsible for breaking down atrazine is GST pi, right up here. Each of the classes, though, have varying enzymatic activity depending on the toxin because they may be specific to certain substrates. And they are also controlled by circadian rhythm genes known as clock and BMAL1. So the specific aims of my project was to determine if atrazine exposure during development affects circadian rhythm of the GST isotypes expression. And we hypothesized that if mice are exposed in utero to atrazine, then we will see dysregulation of the various isoenzymes of GST, which would indicate interruption of circadian rhythm by atrazine. So here's the outline of our study. The first thing we did is we exposed the pups in utero to atrazine via Dame's water, and we had 3 different treatment groups: a 0 parts per billion, a 3 parts per billion, and a 30 parts per billion. Once they were born, we harvested newborn pups' liver tissue at 4-hour time intervals, and we did glutathione S-Transferase protein and enzyme assays, immunoblots, and Q real-time PCR to get mRNA expression. But for BMAL1, we only did the Q real-time PCR to get mRNA expression, but for mu, pi, and alpha, we did everything that is listed above. So a little bit about our enzyme assay. So as you can see, at the left is the isoenzymes of GST, known as mu, pi, and alpha. And the substrate used for each of these, for mu, it was cDNB, for pi, it was ETHA, and alpha, it was cumene. So how it works is there's a thiol group on GSH that GST brings it to, the xenobiotic to. And when GST brings the xenobiotic, the glutathione, you see this thiol group, so more specifically the sulfur, get attached to the xenobiotic. And when this happens, it goes from a reduced to an oxidized state, which allows us to see an increase in absorption. So the first thing that we did was mRNA expression. So we did this by Q real-time PCR, and what we found is that for GST alpha, mu, and pi, the control group, or the 0 parts per billion group, aligned with the previous study done by Zhu. What we found is that at a time point of ZT4 for GST alpha, mu, and pi, there was peak mRNA expression, which is also the same as what this previous research study found. But then what we did is we treated with atrazine at 3 parts per billion and 30 parts per billion. For GST alpha, when we treated with atrazine for 3 parts per billion and 30 parts per billion, we see flatlined mRNA expression. For GST pi, when we treat it with 3 parts per billion and 30 parts per billion, we see flatline mRNA expression. For GST-mu, we see the same thing. When we treat with 3 parts per billion and 30 parts per billion, we see flatlined mRNA expression. So this indicates that atrazine is affecting mRNA expression. But for BMAL1, we see something a little bit different. So again, when we don't have a treatment and it's just the 0 parts per billion or the control group, we see that it aligns with the previous study done by Zhu. This one right here. So at a time point of ZT4, which is 4 hours into the light phase, we see that there's peak mRNA expression in BMAL1, which is the same as what they found in Zhu's previous research. But then when we treat with 3 parts per billion and 30 parts per billion atrazine, what we see is a shift, and we also see another peak in the dark phase. We suspect that this is because BMAL1 is regulated by the redox potential of the cell. And previous research studies done by Lin showed that the electron transport chain between complexes 1 and 3 is being affected by atrazine. So if that's the case, then it could be throwing off the redox potential of the cell and thus throwing off BMAL1. But that's further direction that could be looked at. The next thing we did was our enzyme assay. And what we found is for GST-mu, GST-alpha, and GST-pi, we see this natural fluctuation with 2 peak mRNA expressions at ZT of 4 and a ZT of 16. The ZT of 16 makes sense to us because mice are nocturnal, so realistically, there should be peak enzymatic activity during the dark phase because that's when they're eating and that's when they would need the most detoxification. But the ZT of 4 was kind of confusing, but we found some previous research that supports this that I'll dive into in a little bit. So going with our treatment groups, for GST-mu, when we treated with 3 parts per billion and 30 parts per billion atrazine, we see decreased enzymatic activity. For GST-pi, when we treat with 3 parts per billion and 30 parts per billion atrazine, we see decreased enzymatic activity as well. And for GST-alpha, when we treat with 3 parts per billion and 30 parts per billion atrazine, we see decreased enzymatic activity. But now jumping into the previous research. So this is 2 studies that I found that shows the rhythm of hepatic thiosulfite sulfur transferase, and that's just another detoxification enzyme present in mice. The 2 figures at the right over here shows that when mice goes through development, enzymatic activity changes. So as you can see, with the 4-week, you see these natural two peaks in enzymatic activity, but then with the 8-week, you see this one big peak, and then you kind of just work up to that big peak again. So this indicates that as mice are changing and developing, that their enzymatic activity is also changing, which makes sense because when they're younger, they're constantly eating as they're developing, but as they get older, they start to just eat during the dark phase because they're nocturnal. And again, this left figure here is from that same study, and what we see is this 2 peaks in enzymatic activity like we saw in our study. And this is when the mice are 2 weeks old, so we harvested our mice tissue almost immediately after they are born, so it makes sense why we might have the same results as the 2 peaks because they're probably constantly eating. So in conclusion, what we found is that atrazine exposure is affecting circadian rhythm expression of GST mRNA, circadian rhythm expression of BMAL1 mRNA, and atrazine exposure is also affecting GST enzymatic activity. But why is this all important? Well, if atrazine is affecting circadian rhythm and is disrupting it, then it could be affecting many things in our lives and also in the animals that are drinking the water that atrazine is present in. It could be affecting our sleep schedule, one-to-one eats, hormonal regulation, behavior, and everything that's seen over here that is regulated by circadian rhythm. So some future direction. We could further explore the redox state of the cell because BMAL1 is again regulated by the redox potential of the cell, and you could do this by using the GCMS and looking at metabolic intermediates of atrazine. And then also, another further way you could explore is looking at GST isoenzymes, enzymatic activity changes throughout development. It's kind of what that previous study did with the thiosulfate transferase, but instead we could do it with GST to see if there is age differences in enzymatic activity. And also you could look at gender differences, because it was shown in that previous study too that males and females, their enzymatic activity is different. So those are two ways that you could further explore. I would just like to acknowledge the molecular biology class of 2018 and 2019 for their help with dissections. There is no way we would have been able to dissect all those mice in the amount of time that we needed to without their help. I'd like to thank St. Mary's University Biology Department for providing all the necessary resources to carry out this study, and New England Biolabs for providing the kits to us. And also, I'd like to thank Dr. Deborah Martin for all she did for us and help us run the study and being there for guidance. And here are my references. If you guys have any questions, feel free to reach out. I'd be happy to answer them. Have a great day and stay safe, everyone. Thank you.